Good evening, children.
Good evening, ma'am.
Good evening.
Good evening, ma'am.
Good evening. Yeah, let's recall before we continue. So tell me, what are real numbers made up of? Real numbers is the collection of dash and dash.
Rational irrational numbers.
Correct. Real numbers is the collection of all rational numbers and irrational numbers. Correct. And name the three types of decimals. The three types of decimals.
Terminating, non-terminating but repeating, non-terminating and non-repeating.
Correct. Terminating decimals, non-terminating, repeating, or non-terminating, recurring decimals. And then non-terminating, non-repeating, or non-recurring decimals. Very good. Now, which of these decimals have a P by Q form? Which of these decimals have a P by Q form? Or which of these decimals are a result of a division process? How do we obtain a terminating decimal? A terminating decimal is obtained through a division process. When you divide P by Q, the division comes to an end with a zero remainder, and the quotient so obtained will be a terminating decimal. A terminating decimal is the result of a division process. Upon dividing P by Q, the division process will come to an end with a zero remainder, and the quotient so obtained will be a terminating decimal. Then the other one is the non-terminating repeating decimal, which is also a result of the division process. When you divide P by Q, the division does not come to an end. A remainder or a set of remainders keep happening, keep repeating. And in the quotient, also we see a remainder or a set, a digit or a set of digits repeating themselves in the quotient. A digit or a set of, if a remainder repeats, you will see a digit, one digit repeating in the quotient. If a set of remainders repeat, then a set of digits will repeat themselves in the quotient. So a non-terminating repeating decimal is also a result of the long division process, wherein the division does not come to an end with a zero remainder. In that case, the quotient obtained is a non-terminating but repeating decimal. The other one, non-terminating, non-repeating decimal, is not a result of this long division process. When you divide P by Q, you will never get a non-terminating, non-repeating decimal. You cannot get. That's why we say a non-terminating, non-repeating decimal does not have a P by Q form, which is why it's called an irrational number. A non-terminating, non-repeating decimal does not have a P by Q form because it is not a result of the long division process. It is not the quotient obtained by performing a long division. This non-terminating, non-repeating decimal is not the quotient obtained by the long division process. No. We don't get a non-terminating, non-repeating decimal like that. It's not a result of the division process, which means this non-terminating, non-repeating decimal does not have a P by Q form. No division is happening, no? So it doesn't have a P by Q form. And we understood that we get, then how do we get these numbers? These are the values of square root of imperfect squares, cube roots of imperfect cubes, and so on. And we also understood that pi, the value of pi is a non-terminating, non-repeating decimal, which is why pi is also an irrational number. Okay. So terminating decimals and non-terminating repeating decimals have a p by q form. Non-terminating, non-repeating decimals do not have a p by q form. If a number has a p by q form, if a number assumes a p by q form, it's called a rational number. P by q meaning integer by integer, where the denominator integer should not be 0. So integer by integer form, p by q form is a rational number. And numbers that do not have a p by q form are irrational numbers. If a number does not have an integer by integer form, like square root of 2, is square root of 2 by 1, but this one is not an integer. This is an integer. This one is not an integer. So square root of 2 can be written as square root of 2 by 1, but it is not integer by integer. This one is an integer, but this one is not an integer. So irrational numbers do not have a p by q form. All right. Now, here you see, without actual division, find which of the following rational numbers have a terminating decimal expansion. Now, we are not supposed to perform the long division. We are not supposed to perform the long division. Without performing the long division or the actual division, you need to say if the rational numbers given. Why rational numbers? Because you can see they're all integer by integers, integer by integer form. All the numbers from A to F. Okay, so find which of the following rational numbers have a terminating decimal expansion. Okay. So now take up the first one. Don't write anything. I'll tell you. 15 by 96. The first step is to put the rational number in its lowest terms or the simplest form. First, write the rational number in the simplest form. All right. So 3 5s are 15. 3 32 times. So 5 by 32. Now this one is a simplest form. 5 by 32 cannot be reduced any further. Now take up the denominator. Step 1, write the rational number in its lowest terms. Write it in the simplest form. Next, take up the denominator, 32. Okay. Express the denominator as a product of its primes. So you know 32 can be written as 2 to the power 5. So you do this process. 2 16 times, 2 8s are, 2 4s are, 2 2s are, and 2 1s are, right? So 32 is equal to 2 to the power 5. Now, what are the primes we have in the factorization of 32? We have only 2. 32 can be expressed as 2 to the power 5 into 5 to the power 0. If the factorization of the denominator has primes 2 or 5 or a combination of 2 and 5, then that p by q will have a terminating decimal expansion. Denominator 32. 32 is 2 to the power 5. Okay, which is nothing but 2 to the power 5 into 5 to the power 0. Just show the presence of 5 like that. Okay, so 5 to the power 0 is nothing but 1. So 32 can be expressed as 2 to the power 5 into 5 to the power 0, which assumes this form, 2 to the power m into 5 to the power n, where m and n are whole numbers, where m and n are whole numbers. So if you can write the denominator in this form, if the denominator of the rational number, which is in its lowest terms, okay? So if the denominator can be expressed in this form, 2 to the power m into 5 to the power n, where m and n are whole numbers, then that rational number will have a terminating decimal expansion. If you cannot express the denominator like this, then that rational number has a non-terminating repeating decimal expansion. 15 by 96, simplest form, 5 by 32. Okay, now take up 32. 32 is equal to 2 to the power 5, which is also 2 to the power 5 into 5 to the power 0, which is of the form 2 to the power m into 5 to the power n. So we have 32, in the factorization of 32, we have only this prime 2. I told you the denominator can have primes 2 or 5 or both 2 and 5. 2 or 5, only 2, only 5. like 2 to the power something or 5 to the power something or both the primes 2 and 5. If you can express a denominator like this, then that rational number has a terminating decimal expansion. If it has any other primes other than 2 or 5, then it will have a non-terminating repeating decimal expansion. See the steps here. Right, this is simplest form 5 by 30, 15 by 96. This is simplest form 5 by 32. Don't do anything with the numerator. Write the prime factorization of the denominator alone. Don't do anything with the numerator. Write the numerator as it is. So we have 5 by 2 to the power 5. So the denominator has no prime factors other than 2. Therefore, it has a terminating decimal expansion. And in this slide, I have mentioned the what I explained now. No, I had mentioned in this slide. Condition for P by Q in the simplest form to have a terminating decimal expansion. The denominator Q should be, it should be possible to express the denominator Q in this form, 2 to the power m into 5 to the power n, where m and n are whole numbers. Condition for P by Q to have a terminating decimal expansion. It should be possible to express the denominator Q in this form, 2 to the power m into 5 to the power n, where m and n are whole numbers. And the condition for the rational number to have a non-terminating repeating decimal expansion is Q. You will not be able to express Q in this form. You will not be able to express Q in this form, meaning the denominator Q may not have the factors 2 or 5, or it may have 2 and 5 and some other factor along, some other prime along with them. In such cases, the rational number will have a non-terminating repeating decimal expansion. Yeah, so this is how we present the answer. Simplest form, then express the denominator as a product of primes and observe the primes. So here the only prime is 2. So the denominator has no prime factors other than 2. Therefore, it has a terminating decimal expansion. 11 by 24. The next one is already in the lowest terms. 11 by 24 is already in the simplest form. You cannot reduce it any further. So then the next step is to express the denominator 24 as a product of its primes. So 2 cubed into 3. See, this is the procedure. 2 12s are, 2 6s are, 2 3s are, 3 1s are. So 2 cubed into 3 like this. 2 cubed into 3. So we do find the prime factor 2, but there is 3 along with it. No, there should be 2 or 5 or both 2 and 5. No other primes other than 2 or 5. So you can see the presence of 3 here. The denominator has 3 as a prime factor, which is other than 2 and 5. Therefore, 11 by 24 will not have a terminating decimal expansion. See, we give this answer because the question is, find which of the following rational numbers have a terminating decimal expansion. The question is, which of the following have a terminating decimal expansion? So you'll have to say if it has a terminating decimal expansion or not. Whether it has or not. So this one will not have a terminating decimal expansion. That means it has a non-terminating repeating decimal expansion. The denominator has 3 as a prime factor, which is other than 2 and 5. Therefore, 11 by 24 will not have a terminating decimal expansion. 27 by 80. So it's already in the simplest form. You cannot reduce it any further. Prime factors of the denominator 80. So the denominator has 2 and 5 only as its prime factors, terminating decimal expansion. Am I clear, children?
Yes, ma'am.
Okay. 16 by 125. It's already in the simplest form. You cannot reduce it any further. 16 by 125. You cannot simplify it any further. So find the factors of the denominator. 125, 5, 25 times. 5 5s are 5 1s are. So 125 is 5 cubed. So the denominator has no prime factors other than 5. Or you can say the denominator has only 5 as its prime factor. So it has a terminating decimal expansion. The power of 2 or 5 can be anything. 2 raised to any power, 5 raised to any power. The denominator should have only 2 or 5 or both 2 and 5 as its primes. 2 can be raised to any power, 5 raised to any power. See, reducing it is very important, you know. Reducing is very important. 21 by 112. So 21, take the smaller of the two numbers, 21. Now 21 you can simplify using 3 tables and 7 tables, right? 3 7s are or 7 3s are. Now this one 112, 2 plus 1 3, 3 plus 1 4. It's not divisible by 3. By the test of divisibility of 3, the sum of the digits 2 plus 1 3, 3 plus 1 4. 112 is not divisible by 3. But check by 7. 112 by 7. 7 1s are 4, 7 6 are 42. Yeah. So it's possible to simplify this rational number because the numerator and denominator have 7 as a common factor. 7 is a common factor of the numerator and denominator. So 7 3s are and 7 16 times. 3 by 16. So that's very important. You need to express the rational number in the simplest form and then find the prime factors of the denominator. So simplest form is 3 by 16. As I told you in the tables of 7, 7 16 times, 7 3s are, so 3 by 16. And now 16 is 2 to the power 4. So there is no other prime other than 2 here. Therefore, 3 by 16 or 21 by 112. 3 by 16 or 21 by 112. They're equivalent fractions, right? These were equivalent fractions. So if this one has a terminating decimal expansion, this one also has a terminating decimal expansion. So 3 by 16 or 21 by 112 has a terminating decimal expansion. 4 by 35. 5, 7. 35, 5 into 7, 7. So the denominator has 7 as a prime factor, which is other than 2 and 5. So it will not have a terminating decimal expansion. There is this prime factor 7, which is other than 2 and 5. So 4 by 35 will not have a terminating decimal expansion. So that's about, deciding or how to decide if the given rational number can have a terminating decimal expansion or not. Okay. So first simplest form, then prime factors of the denominator 2 or 5 or both 2 and 5. Then it will have a terminating decimal expansion. Any other prime other than 2 or 5, non-terminating, repeating decimal expansion. And because they are all P by Qs, non-terminating, non-repeating decimal is cannot be the answer because A non-terminating, non-repeating decimal does not have a P by Q form. If it is P by Q form, it's either terminating or non-terminating repeating. Okay. So the question of meaning why can't it be non-terminating, non-repeating will not arise there. Because you're given P by Qs, they're all rational numbers. So if the rational number does not have a terminating decimal expansion, then it should have a non-terminating repeating decimal expansion. So there is no question of why can't it have a non-terminating, non-repeating decimal expansion? Because it's a rational number. It cannot, it will not have a non-terminating, non-repeating decimal expansion because that is of an irrational number, which does not have a P by Q form. So that's about it. So if you have to mention the rule, Q, the denominator Q, you should be able to express the denominator Q in the form 2 to the power m into 5 to the power m, n, where m and n are whole numbers. This is the rule. If you cannot express Q in this form strictly, then it will have a non-terminating repeating decimal expansion. Now, inserting rational numbers, we have learned it earlier, so we'll not do this in detail, though you have it. You will find questions like this happening in your tests and exams. So I'll just share the answers with you later. You can to help yourself. I'll just take you through the slides. Have a look. So insert 5 rational numbers between 0 and 0.1. 0 and 0.1. Okay, so I have inserted 0.01. See, between 0 and 0.1. So I have taken 0.01. Okay, then 0.003. 0. See, you just put it between 0 and 0.1, right? So 0. Just put a 0 and write anything. Or put another 0 and write anything. You can even write 999. That will be, less than 0.1. 0. Just add a 0 and write whatever you want. Or 0.00 and write whatever you want. Seriously, whatever. You can even add 9s. So these numbers will be between 0 and 0.1. So I have taken 0.01. So we are safe, no? We are between that. 0.003, 0.011, 0.09. You can see that 0, that's very important. 0.0023. So after writing the decimal numbers, put them in their P by Q form. So what is 0.01? 1 by 100. 0.003, 3 by 1000, right? Because you'll have to insert rational numbers. Don't leave them as decimals like this. Put them in their P by Q forms. Put them in their P by Q forms. Please ask me. If I'm not clear, please ask me. Okay. Between 1.3 and 1.4. 1.3 and 1.4. So to insert, you can just, increase the number of decimal places. So like 1.3, you can just add a 0. Like it's 1.30, but you just read it as 30. 1.30. You're not supposed to read like that. It's 1.30, but just take it as 1.30, and this will be 1.40, 40. So now between 30 and 40. So it will be 1.31, 31, 32, 33, 34. Just increase the gap, the space between the two numbers. 1.3 can also be written as 1.30. 1.4 can be written as 1.40. Now the decimal part, 30, 40. And the numbers between 30 and 40, 31, 32, 33, 34, 35. So you can write 1.31, 1.31, 1.32, 1.33, and so on. Or you can still increase the space between the numbers by adding one more zero like this. So 1.300, 1.400. See, they should have equal number of decimal places. Take care. So this is 300, this is 400. 3 digits after the decimal point, 3 digits after the decimal point. $300, 400. So 301, 1.301, 1.302, 302, 303, 304 till 399 you can write. You can still increase the gap. Okay, so 1.3, 1230. So 3000, 1.4, 123. So 4000, 3000, 4000. Oh, so many numbers between them. 3001, 3002. So 1.300. Yeah. And this is 4000, right? So 1.3999, 3999. You can go on till this number. So this clearly, this from this you clearly understand that there are infinitely many rational numbers between two given rationals. There are infinitely many rational numbers between two given rationals. So to write the first one, 1.31, I have taken 1.30. I've treated the numbers as 1.30 and 1.40, and I've inserted 1.31, 31. For the second one, 1.300 I've taken 300 and 400. 300, 400. For the second one, this one. 1.300, 1.400, right? So between this is 1.379. Between 300 and 400, 379. This also is between 30 and 40, 1.33, between 1.30 and 1.40. This one also, 30 and 40, 39. This one is 309, between 300 and 400, 309. So like this, you can increase the number of decimal places and insert as many numbers you want. After writing the decimal numbers, put them in their P by Q form. And you can see that I have look at the numbers I've used. So be careful when you write the digits, see that you're going to get denominator 10, 100, 1000 and so on. So let the numerator not end with 2, 5, because in that case, we'll have to again simplify. So don't spend too much time on this. So you can, I think, understand. Look at the numbers I've used, 1.33. So when the denominator is 10, 100, you will not be able to simplify it any further. Because the denominator 10 or 100, 10, 100,000 will be divisible by 2 and 5. So make sure that numerator is not divisible by 2, and 5. Then you can just save time. Otherwise, you'll have to simplify. See, supposing you write 1.388, okay? Then you'll have to write as 1388 by this 1000, and then you'll have to reduce it, because you should never leave a rational number in the reducible form. You should reduce it. You should never leave a rational number in the reducible form. It should be in the irreducible form. You should not be able to reduce it any further. So then you need more time, no? You'll have to simplify this. See, you can write, not that you should not write, just that if you use, meaning write such numbers, you will have to spend a little more time in simplifying them, that's all. So in my examples, you see that I've used the digits carefully so that, simplification is not possible. So you can just write the rational numbers and go to the next one. 3 by 8, 2 by 5. So, you'll have to make them like fractions. You'll have to make them like fractions, bring them to the same denominator. Okay, so 3 by 8, 3 by 8 is 15 by 40 and 2 by 5 is 16 by 40. Find the LCM, write their equivalent fractions, bring them to the same denominator. So 40, 15 by 40, 16 by 40. Okay, now there is no space, no? You'll have to insert rational numbers between 15 by 40. 3 by 8 is 15 by 40 and 2 by 5 is 16 by 40. Now how to insert? There is no space between the numerators, 15 and 16. You can write 15.1 by 40 and then you can write actually. See, 15 and 16, 15.1, no? 3 by 8 is 15 by 40. 2 by 5 is 16 by 40. So numbers between this 15.1 by 40, 15.3 by 40, 15.7 by 40, 15.9 by 40. And after this, 15.1 by 40 is nothing but 151 by 400, right? And then 153 by 400, 157 by 400, because when you shift the decimal point, it becomes 400 in the denominator, 159 by 400. You can do this. Or still increase the space in the numerator. So I've multiplied each of them by 6. Multiply the numerator and denominator by 6. So 15 by 40 becomes 90 by 240. This one becomes 96 by 240. Now you can see that the gap between the numbers and the numerator has widened. When you do this, we've increased the space between the numbers and the numerators, 90 and 96. Now you have space. So 91 by 240, 92 by 240. After doing this, you should reduce it. First LCM, you get these numbers, but there is no space between the numbers and the numerator. So you want to widen the space. For that, again, you multiply and divide like this, 6 by 6 for both. So now it is 90 by 240 and 96 by 240. Now between 90 and 96, write the numbers. 91 by 240, 92 by 240, 93 by 240, 94 and 95. And this 94 by 240 should simplify. Cancel and it's 23 by 16. This one also cancel, it's 31 by 80. This one cancel and it's 47 by 120. This one cancel and it's 19 by 48. As I told you, you should never leave a rational number in the reducible form. You should write it in its lowest terms, in the simplest form. So this is the simplest form, 23 by 60 and so on. So the first one was a 0 and 0.1. I told you 0 point, just put a 0 and then write whatever you want. That's about the first one. 1.3 and 1.4, you can make it 1.30, 1.40. Now 30 and 40, you can insert numbers. Then you can add one more 0. So 300 and 400 and insert numbers. This one is using LCM. Minus 1.5. Minus 1.5. Half is 0.5. So minus 1 and half. This is 0 and this is 1 by 2. This is 1. So you can see the numbers, no, between minus 1.5. So I have written minus 0.5, minus 0.5, and then minus 0.1. Then what's the 0.1? Then 0.3. You can also use the concept of LCM and do it. So there is no, specific approach. It's not that you should do this like this only. So there are, when, certain things, questions like this have more than one approach. So you can use your own method. You can use the concept of LCM. You can bring them to the same denominator and do it. Or I have turned half into its decimal form, 0.5, and then I visualized the rational numbers between using the number line. Just visualize. This is 0.5, no, half. This is 1. So what are the numbers line? There are so many numbers. So I have written minus 0.5 here, minus 0.5, which is between minus 1 and 0.5, right? And then minus 0.1, minus 0.1, and then 0.1, and then 0.3, like this. And please write them in the P by Q form. So I wrote the decimal number and then minus 5 by 10, which can be reduced to minus 1 by 2. Then this one, which is minus 1 by 10. I've also written 0. I missed to read that. I've also written 0. That's also between these two numbers given. Okay. 0.1, which is 1 by 10, 0.3, which is 3 by 10. Yeah. So that was about inserting rationals between two given rationals. Now we learn how to put rational numbers, or no. We learn how to write a terminating decimal in the P by Q form and how to write a non-terminating repeating decimal in the P by Q form. So 0.235. 0.235. This is familiar to you. Okay, so this one is a terminating decimal, and we know how to write this in the P by Q form. There's nothing but 235 divided by 1,000, because you'll have to shift the decimal point by 3 places, right? So 3 zeros. 0.235 is equal to 235 divided by 1 followed by 3 zeros, because we'll have to move the decimal point by 3 places to the right. And then simplify and write it in its lowest terms. That's about writing a terminating decimal. This is how you write a terminating decimal in the P by Q form. And this is familiar to us. Now, the second one is 0.235 recurring. Now, this one is a non-terminating repeating decimal. How do we find its P by Q form? So we learned that procedure. Class, who is the emoji? Raise your hand. Thank you, children. Yeah. Yeah, the first step is, now what is 0.235 recurring equal to? This means 0.23535, because the bar is placed only on top of the digits 3 and 5. The bar is placed on top of the digits 3 and 5, right? So 35, 0.235353535, going on forever. This is the meaning. 35 repeats endlessly. Okay. So let x or y, z, any variable, let x be equal to 0.23535. Just write it about 3-4 times. There is no, like, there is nothing like you'll have to write it 2 times or 3 times. Just write it 3-4 times. Okay, so let x be equal to the given number, the given decimal number. Let x be equal to 0.2, 35, 35, 35, 35. I've written it 4 times and then place the dots. Don't forget to do that because it goes on endlessly. Now, how many digits repeat themselves? 2 digits. The bar is placed on top of how many digits? 2 digits. So the next step is to find 100x. If the bar is placed on top of 1 digit, then multiply this equation by 10. See, this is the equation. This is equation 1. This is equation 1. Let x be equal to 0.235353535 goes on. This is equation 1. Now we need to find the second equation by multiplying the first equation by 10 or 100 or 1000 or 10,000. You will have to find 10x or 100x or 1000x or 10,000x. Now how to decide what to find? So for that, look at the bar. The bar is placed on top of how many digits? 2 digits. So 2 digits meaning 100, 2 zeros, 100. So next step is to find 100x. 100x. If the bar is placed on top of only 1 digit, then 10x. Find 10x. So here 100x because it's placed on top of 2 digits. So 100x. So x into multiply this equation by 100 on both the sides. Multiply this equation by 100 on both the sides. Okay, so x into 100, 100x is equal to multiply this one by 100. So what will happen? The decimal point will be shifted by 2 places, right? So 100x will be equal to 23 point. Be very careful. See here, the decimal point moves by 2 places to the right. So see where it is now. 23 point. What is after 23.5? 35, 35, 35, repeating. Is this part clear, children? This is equation 2. The second equation is got by multiplying the first equation by 100. Multiply the left hand side and the right hand side by 100. X into 100, 100x is equal to multiply this one by 100. So 1, 2, it becomes 23.5, 35, 35, 35, going on forever. Please acknowledge. Say yes or no, children. Understood?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Ma'am, I'm
Yes.
doubt. Can you please repeat that again because I'm very confused.
Okay. Sure. Shreya, let me do one thing. Let me just finish it and come back. Thanks for asking. I'll just
sure,
finish it
ma'am.
and I'll just finish the procedure and come back.
Okay,
Now,
ma'am.
yeah. Now equation. Now we'll have to subtract equation 2, equation 1 from equation 2, which means equation 2 minus equation 1 gives. All right. So we'll write equation 2 first. That is 100x is equal to 23.5353535. And then we'll write that first equation. X is equal to 0. Place the numbers carefully. You'll have to align the decimal point. You'll have to align the decimal point. Let me align it. So 0. Okay. So 2, 3, 5, 3, 5, 3, 5. The first equation, children. See the first one. This one. 0.2, 3, 5, 3, 5, 3, 5, 0.2, 3, 5, 3, 5, going on forever. See, the first one, this one can have an extra 3, 5. That's okay. 3, 5 is going on forever. Not that the number of 3, 5s in the first one and the second one should match. There are infinitely many 3, 5s. So don't try to match the number of 3, 5s and all that. Whatever you see here in these two equations, just write it. That's all. Now subtract. Subtract. Now, can you see from this portion in both the equations, it's 3, 5 going on forever. So this one will get cancelled. Cancelled meaning when you subtract, will keep getting 0, right? See here. Let's subtract 5 minus 5, 0. 3 minus 3, 0. 5 minus 5, 0. 3 minus 3, 0. 5 minus 5, 0. So like this one gets cancelled. This part in the two numbers. Now 5 minus 2, 3. 100x minus x is 99x. 99x. 100x minus x is 99x is equal to 23.3. Why did I slash this part? Because on subtracting, you'll only get 0. So 5 minus 2, 3. 23 minus 0 is 23. Now 99x is equal to 23.3. In other words, 93x is equal to 233 by 10. 233 by 10. Right? So x is equal to 233 divided by 10 into 99. The 99 comes for division. So x is equal to, is it divisible? 3 plus 3, 6, no. So see, writing the rational number in the simplest form is your job, okay? So if it's not in the simplest form, you should help me. So 233 by 990. Now you can use your calculator if you have one beside you and check. So 233 divided by 990. Yes, the calculator says it is 0.235353535 going on. So this is the P by Q form. When you divide 233 by 990, the quotient, the division will go on forever. You will not get zero remainder. And the quotient will be 0.235 recurring. So this is the P by Q form of the given non-terminating repeating decimal. The given non-terminating repeating decimal is this one. And using this procedure, we found its P by Q form, 233 by 990. When you divide this, the quotient will be this one. Remainder will not be 0. Because 3, 5 is repeating, 2 digits are repeating, no? 2 different remainders will repeat themselves. 2 different remainders. Say, for example, something like, say, 4 and 7. 4, 7, 4, 7, 4, 7. The remainders 4, 7, 4, 7 will keep happening. Will keep repeating. Yeah, so I'll just tell you this one now. Yeah. So first assign this one to x. Let x be equal to 0.2. Since 3, the bar is placed on top of 3, 5, 3, 5, 3, 5, 3, 5. You can write it 3 to 4 times and then place the dots. Now the bar is placed on top of 2 digits. So we need to multiply this equation by 100. For that, multiply x by 100. Multiply the left-hand side, which is x, by 100. So 100 into x, 100x. Multiply the right-hand side, also by 100. You're multiplying this equation by 100 on both the sides and getting a new equation. This one is equation 1. And you're generating equation 2 by multiplying equation 1 by 100 on both the sides. So when you multiply this one by 100, so now what is 0.235 multiplied by 100? Supposing we'll have to do this. What's the answer? It's 23.5. When you multiply 0.235 by 100, the answer is 23.5. So when you multiply this one by 100, the decimal point shifts here. 1, 2. See here, x is equal to, this one will remain. Here, the decimal point will not shift. I'm just showing you here. X is equal to this one will remain. Here, the decimal point will not shift. In 100x, I'm telling you what you should write. So when you multiply by 100, this decimal point 1, 2, it will shift here. So what's the number you have? 0, 2, 3. That means 23.5 and 3 5s. 3, 5, 3, 5 going on forever. This is the second equation. This is the second equation. Have a look at the answer here. Now, how far have you written your classwork, children? Only the introduction part, right?
Yes, ma'am.
Yes, ma'am. Whatever
Yes,
you
ma'am.
had
The
sent on the.
pictures that you sent to us.
Yeah, correct. Correct. So do one thing, don't continue in your class work. I'll tell you, just get some sheets or a rough notebook and do it in that. I think I haven't shared the notes further. So you will not have it in the order. So you don't write in today's work, don't write in your classwork book. Do it in a rough paper or some other notebook. I'll send the notes today so that you can write it. Yeah, have a look at this. This is for the first one. Why don't you just practice this one in your book? Just scribble and try to understand better. The next one is a test. The next two questions will be a test. That's all is the idea. That's all, nothing else I have to say. If the bar is placed on one digit, 10x, two digits, 100x, three digits, 1000x. That's all.
Ma'am, then what about 0.235, ma'am? Just the first one, 0.235. What about that, ma'am?
Here,
Oh, okay, ma'am.
Ma'am, so the notes you'll be sending us today, it'll be all the questions we did in class, but in order.
yeah, correct.
So you have to rewrite all of that in our notebook.
Rewrite.
I mean, sorry,
No,
write all of it in our normal classwork.
correct, correct. Yes, yes, yes. Yeah, you can just take a screenshot of this one, keep this for reference and try this one. Do this.
Ma'am, can you please go to the last slide for a second? Thank you.
Yeah.
Thank you, ma'am.
Yeah. Yeah, please work this. I'll just get back. Ready with the answer, children?
Yes, ma'am.
Very good.
Yes, ma'am.
Yeah. Yeah. Tell me for the terminating decimal. The first one, 175.175175 is equal to, what's the P by Q form? I don't want the steps. I just want the final answer.
It's 7,007,007 divided by 40,000.
7 0 0 7
007 divided by 40,000.
Okay, nice. And for the second one, 0.175 recurring. So you had to multiply x, that you had to multiply the x equation with which number?
1,000.
1000. 1000, correct. 1000x. Yeah, what's the P by Q form?
Ma'am, I got 175 by 999.
Okay. Okay, I got this one is from Aishwarya. What about the others?
Same answer, ma'am.
Same answer, ma'am.
Okay.
Got the same answer.
All right, let's check. 175 by 99, correct? Lovely. 7007. Very good. That's it. See, you got it. Very nice. So 175.175175 is equal to, just move the decimal point. 1, 2, 3, 4, 5, 6. So 6 zeros in the denominator. 1, 2, 3, 4, 5, 6 zeros in the 6 zeros in the denominator. And then you'll have to simplify. Reduce it in the tables of 5 and yeah, just go on like that. And this is the simplest form. So when you divide this number by this number, the division will come to an end with a zero remainder and the quotient obtained will be 175.175175. That's it. That's all. 175.175175. That's it. On dividing this one by this one, the remainder will come, sorry, the division will come to an end with a zero remainder and the quotient obtained will be this. Yeah, the second one, let x be equal to 0. Okay, the number given is 0.175 recurring. So let x be equal to 0.175, 175, 175. I told you, write it about 3-4 times. Okay, so 175, 175, 175. It goes on like that. Goes on like that. And we call that equation 1. Now, since the bar is placed on top of 3 digits, the next equation is by multiplying the first equation by 1000. So x into 1000, 1000x is equal to, multiply this one by 1000. So 1, 2, 3, 175 point, because when you multiply this one by 1000, 1, 2, 3, the decimal point moves here. 175.175, 175, it goes on like that. So 175.175, Now don't tell me the decimal point comes here, no? So we have only 2 sets of 175 here, visible here. But I have written how much? 1, 2, 3. Now don't ask me why did you write 1 set extra? There are many. There are many. So you can just write. I'm just trying to match the decimal part. That's all. I'm just trying to match the decimal part. If you want, you can put one more here. Then just put one more and then dots. Okay, so that shouldn't be a doubt or any sort of confusion. When you multiply by 1000, you get 175.175. You can write how many ever times you want. See here. The decimal point comes here. After this, what do you have? 175. 175. How many times? Endlessly. So you can write it how many ever times you want. That is the second equation. Now equation 2 minus equation 1 gives, write them one below the other and subtract. So 1000x minus x is 999x. And here when you subtract, the decimal portion is 175, 175, 175 in both. So gets cancelled. So 175 minus 0 is 175. So x is equal to 175 by 999. So what is x? X is nothing but 0.175 recurring. X is equal to this, meaning we had assigned this one to x, right? So that means 0.175 recurring is equal to 175 by 919. Yeah. Not this one. Yeah, do this. Try this one, children. Done, children?
The last step, ma'am, in the last step.
Okay. Aishwarya, I think your mic is enabled. Kindly disable it. Yeah. 1.239 is equal to
1,239 by 1,000.
not 1 point. 1,239 by 1,000. Right? Yeah. What about this?
31 by 25.
1. Lakshana, come again.
31 by 25.
31 by 25. 31 by 25. And yeah, see, Lakshana, one more thing. How can you get 25 in the denominator? 25 is 5 square, right? So the denominator is the only prime. The only prime factor in the denominator is 5. Then it will have a terminating decimal expansion, right? But this one is non-terminating repeating. So this is not possible.
Ma'am, I got minus 12.84 by 9.
Read the digits. Don't read the number as a whole. 1,
2.84.
no, not clear. 125 by 4.
No, ma'am. 12.84 by 9.
9.
Yes, ma'am.
Okay.
Minus 1284. Minus 12.84.
No, no.
Ma'am, I'm getting 279 by 225.
279 by 225.
225.
279 divided by 225. No. Yeah, this is, no, yours is right. 279 by 225. Yes. Aishwarya, sorry. Yes. Not this.
Oh,
1
okay.
point. Yeah. 279. Sorry. I didn't do it properly with the calculator. By 225. Okay, Lakshana, you said 31 by
He said
25.
30.
Lakshana, I'm sorry, please come again. What did you say?
31 by 25.
1 second. 31 by 25. 1 second. Oh, 30. I didn't divide it correct. Oh, yes, Lakshana. Lakshana, I'm sorry. Yes. With the calculator, I went wrong calculating. So I have to tell you something else also about this. Yeah, the others, please check. So 1.239999999. Now for such decimals, the P by Q form will be equal to this value. When you round it off, what do you get? 1.239 recurring. When you round off, when you remove the nines, it will be rounded to 1.24, right? 1.24. So the P by Q form, the P by Q form of this decimal number will be equal to this value 1.24. Always. Now for 1.9, you try for 1.9 recurring. The P by Q form for 1.9 recurring, something like 13.1769 recurring or 90, 9 recurring, 13.1769 recurring. For all these, you will see that the P by Q form, the denominator will have prime factors 2 or 5 or both 2 and 5. Okay, I hope the others finished. Yeah, please check. So since only one digit repeats, 10x. Yeah, please check your steps. 9 recurring, 9 going on forever. So when you round off, you'll get 1.24. 1.24. So when you divide 31 by 25, you will get 1.24. You will not get 1.23999. You will get 1.24. Please check. So this is X. X is equal to 1.23999 going on forever. Multiply by 10 because only one digit repeats. So 10x will be equal to 12.39 recurring. 10x is equal to 12.39 recurring. Now equation 2 minus equation 1. 10x minus x is 9x. And here place the digits, place the numbers carefully. Make sure that the decimal point is aligned. So what happens here? This 9 and 9, 0, 9, 9, 0. So 9 minus 3, 6. 3 minus 2, 1. 2 minus 1, 1. And this 1 on subtracting. On subtracting, 9 minus 9, 0. I have not written that, that's all. 9 minus 9, 0. 9 minus 3, 6. 3 minus 2, 1. So 9x is equal to 1116. 1116 divided by 100. Divided by 100. So then the 9 comes for division. X is equal to 1116 divided by the 9 comes for division. So 9 into 100, 900. 9 comes down here. So 9 into 100, 900. And then reduce it. Reduce it. So use a test of divisibility. You can see here 9 plus 7, 16. 16 plus 2, 18. The sum of the digits is 18. And here 5 plus 2, 7. 7 plus 2, 9. 9. So it's divisible by 3. Both the numerator and denominator are divisible by 3 by the test of divisibility. The sum of the digits 18 and 9. Then again you can divide by 3. You can again divide by 3 because both these numbers are divisible by 9. It's actually 9 31 times and 9 25 times. So x is equal to 31 by 25, which means x is 1.239 recurring is equal to 31 by 25. Yeah, but this one is a non-terminating repeating decimal. This is an exception. Okay, this one is a non-terminating repeating decimal. So the P by Q form, the denominator will have primes other than 2 or 5. But here you see the prime is 5. The prime factor of the denominator is 5. So this happens in cases where we have 9 in the end, 9 recurring. This will happen in all the cases where 9 repeats. Like this one, 1.239 recurring, because it's rounded off to the next number. And then that way it looks like a terminating decimal. It looks like a terminating decimal. 1.239 recurring, no? So when you round off, it becomes 1.24. So its P by Q form will be equal to this value. 31 by 25 when you divide, you will not get 1.239 recurring. Instead, you will get 1.24. So there's an exact exception. Okay, that's about putting numbers in the P by Q form. Yeah. Work this with the help of the slide, and the next one is a test. Work this one with the help of the slide. The next one is a test. This is a test. This one. Practice this one. Yeah, finish this one.
Yes, ma'am.
Yeah. Try this.
Ma'am, 164 by 99.
164
by 99.
Okay. Perfect. Good.
Ma'am, even I got the same answer.
Very good. Is it possible for both of you to share your pictures on WhatsApp?
Yes, ma'am, but it is in rough work. Is it fine?
Yes,
That's
ma'am.
okay. That's okay. That's okay. Yeah, what's happening with others? About to get it?
Ma'am, even I got 164 by 99.
I also got 164 by 99.
Very good.
Same answer, ma'am.
Very nice. Yeah. Check your steps. So the question is to write this one in the P by Q form.
Ma'am, here we don't need to simplify 14 by 11, right, ma'am? As 14 by 11, right, ma'am?
No, but later for, yeah, here I've simplified, but later to add, I have taken 126 by 19. It's okay if you didn't write this. I understand your question. It's okay if you didn't write this. Yeah. Because they have the same denominator, no? So you can just stop here. So A is 0.383838. 2 digits recurring. So you'll have to find 100x. So when you multiply A by 100, you'll get 100A. And this number by 100, 1, 2. Here the decimal point moves. So it'll be 38.383838. So 100A is 38.3838 going on forever. A is 0.3838. On subtracting, the decimal portions will get cancelled because the decimal portion is the same in both. 3838 going on forever, right? So it'll be 0. Like the decimal part in both gets cancelled. When you subtract, you will get 8 minus 8, 0. 3 minus 3, 0. 8 minus 8, 0. 3 minus 3, 0. 0.38 minus 0 is 38. Yeah.
Yes,
100A minus A is 99A. 100A minus A is 99A is equal to 38. So A is equal to 38 by 99. And here B is equal to 1.272727 going on forever. Again, 2 digits repeating. So 100B, 1.27, sorry, 127.2727 recurring. Subtract 100B minus B is 99B. And here again, 7 minus 7, 0, 2 minus 2, 0, 7 minus 7, 0, 2 minus 2, 0. So you can just slash the decimal regions. You can just slash the decimal regions. 127 minus 1, 126. Now add. Add this and this. So the answer is 164 by 99. 164 by 99. All right. Yeah. Look at this question. Given, don't write, okay? We'll just listen. Given 1 by 13 is equal to 0.076923 recurring. Find the decimal expansions of 2 by 13, 3 by 13, 4 by 13, so on, up to 12 by 13, because 13 by 13 is 1. Without actually performing the long division. You should not perform the long division. You should not divide 2 by 13 like this and find the decimal value. No. You're given the value of 1 by 13. Using this, you should find the decimal expansions of 2 by 13, 3 by 13 till 12 by 13. Okay. So 1 by 13 is equal to 0.076923 recurring. Now 2 by 13 can be written as 2 by 13 can be written as 2 into 1 by 13. 2 by 13 is equal to 2 into 1 by 13. So that is 2 into the decimal expansion of 1 by 13 is given to us 0.076923 recurring. Now the bar is on top of 6 digits, right? Okay. Now multiply. Do the regular multiplication. 0.076923 into 2. The regular multiplication. We'll have to multiply these two. 0.076923 multiplied by 2. The regular multiplication. 2 3s are 6. 2 2s are 4. 2 9s are 18. 8 1 carried over. 2 6 are 12 plus 1 13. 3 1 carried over. 2 7s are 14 plus 1 15. 5 1 carried over. 2 zeros are 0 and that 1 plus 1 point. 2 into 0 is 0. 2 into 0. You'll have to multiply. 2 into 0 is 0. And how will you place a decimal point? After the decimal point, 1, 2, 3, 4, 5, 6 digits. So 1, 2, 3, 4, 5, 6 digits. That's what we do now. After finding the product. After the decimal point, 6 digits. So place the decimal point here. And you see there are 6 digits after the decimal point. So when you find the product, it is 0.153846. Now the bar here is on top of 6 digits, right? So same 6 digits here also. So when you divide 2 by 13, this is what you will get. Okay, use a calculator, I'll find 2 by 13. 2 divided by 13 is equal to 153846. 153846, again 153846, 153846, going on forever. Same for everything. So 3 by 13 is equal to 3 into 1 by 13. 3 by 13 is equal to 3 into 1 by 13. So that is 3 into the value of 1 by 13 is given 0.076923 recurring. Now multiply this number and this number as usual. And in the product, place this bar on top of the last 6 digits after the decimal point. That's all. So go through this. See, everywhere the answer will be 0 point only because 13 by 13 only is 1. See, you will not get, see, 13 by 13 is 1. So till 12 by 13, you will get 0 point something. 13 by 13 is 1. So 12 by 13 also will be 0 point something. So we'll just take this one for example. 7 by 13 is 7 into 1 by 13. So 7 into 1 by 13 is given 0.076923 recurring. So multiply. You get this as the product. Place the bar. Because here the bar is on top of 6 digits, right? 1, 2, 3, 4, 5, 6. So same thing here also. So that's about this one. Find 3 different irrational numbers. Find 3 different irrational numbers between 5 by 7 and 9 by 11. Irrational numbers. Irrational numbers meaning non-terminating, non-repeating decimal expansions. You'll have to find 3 irrational numbers. Non-terminating, non-repeating decimal expansions between 5 by 7 and 9 by 11. So you will have to divide 5 by 7 and find the decimal expansion of 5 by 7. Divide 5 by 7. 5 by 7 is rational because P by Q form. 5 by 7 is rational. 9 by 11 is also rational because P by Q form, integer by integer form. 5 by 7 and 9 by 11 are rational numbers. You will have to insert 3 irrational numbers between these 2 rational numbers. We know that between 2 real numbers, there are infinitely many real numbers. Between 2 real numbers, there are infinitely many real numbers. So we have to insert 3 irrationals between these 2 rationals. So whenever we have to insert irrational numbers, we'll have to find the decimal values. So 5 by 7, divide and find the decimal value of 5 by 7. 9 by 11, divide and find the decimal value. Okay, I'll use this one. Okay, so division, I don't have to explain. So perform the long division. You will have to perform the long division. Okay, so 5 by 7, you see here, 5 by 7, you'll have to divide and find the decimal expansion. 9 by 11, divide and find the decimal expansion. So when to stop the division process, you need to go on till you, get the same digit repeating in the quotient, or when you realize that the remainders have started repeating. Like you see here, the remainder 5, 1, 3, 2, 6, 4. Again 5, 1. 5, 1, 3, 2, 6, 4. Again 5, 1. So you will get 3, 2, 6, 4. And in the quotient 7, 1, 4, 2, 8, 5. Again 7. 6 different remainders. You can see 6, 1, 2, 3, 4, 5, 6. 6 different remainders. The remainders are 5, 1, 3, 2, 6, 4. The remainders 5, 1, 3, 2, 6, 4 will keep repeating. Because see, after that again you get 5, 1, 3, 2, 6, 4. Again 5, 1, 3, 2, 6, 4. So we have 6 different remainders repeating themselves in the division process. So when you look at the quotient, you will find 6 digits repeating. So the digits are 7, 1, 4, 2, 8, 5. Again, 7, 1, 4, 2, 8, 5. Because that you can understand, because once the remainder start repeating, the digit in the quotient also will start repeating. So you again get a 7 here. That means you continue the division, you will get 1. Then you will get 4, 2, 8, 5. Again 7, 1, 4, 2, 8, 5. 6 different remainders repeat in the division process. So you will find that in the repeating block, in the quotient, in the repeating block, you will have 6 digits. In the quotient, in the repeating block, after the decimal point, in the repeating block, you will have 6 different digits repeating themselves. A set of 6 digits will repeat in the quotient because we have a set of 6 digits repeating as remainders in the division process. So you should not abruptly stop the division. You should not simply stop after 2, 3 steps. You must wait till the remainder repeats. And you must confirm that you should confirm. See, like I did 5, 1. I got remainders 5, 1, 3, 2, 6, 4. I got 5, but I didn't stop there. I just want one more. You can actually stop, but I just did one more step. I just confirmed. Yeah, I'm getting 1. Yeah, I'm getting 5, 1. Yeah, stop. Here also, see, I got remainders 9, 2. Again 9, 2. You can stop, children. I'm saying, like, once you get 9, you can stop there. Yeah. If you want to be damn sure or double sure, just do it. So 9, 2. Again 9, 2, 9. You can see. So 9, 2, 9, 2. So 2 different remainders, 9 and 2. 2 different remainders, 9 and 2. Repeat. Okay. So in the quotient, you see the 2 digits, 8, 1, 8, 1. 2 digits repeat in the repeating block after the decimal point. So you should not stop. See, like at this point, you should not stop the division. Okay, remainder 2. Let me stop here. It's not like that. You should not stop there. You must wait till the remainder repeats itself. So 5 by 7 is equal to 0.714285. Sorry, I shouldn't put the 7 here. I'll correct this. I'll correct this one. You should not write the 7 here. Okay, so 0.714285. That's all. Okay. Oh, sorry. This also 0.81 recurring. 0.81 recurring. Yeah. So 0.81 recurring. Now insert the irrational numbers. So remember, to insert irrational numbers, you need the decimal expansions of the border numbers. You need the decimal expansions of the border numbers. When I say border numbers, I'm talking about 5 by 7 and 9 by 11. You need the decimal expansion of 5 by 7. You need the decimal expansion of 9 by 11. So now between these two, so you can just treat this one as just see the first 2 digits, 7, 1, and this is 8, 1, no? Look at the first 2 digits, 0.71, and this one is 0.81. So it's like 71, 81, 0.71, 0.81. Okay, so you can see here 0.72. I've written 0.72 and then something after that. Then 80, 0.80, 79. Can you see? I'll tell you, I haven't completed. So you should start like that, 0.81. 0 point, you can see 0.71 here. Here it is 0.81. So between 71 and 81, 0.72, 73, 0.74, 0.75, 0.76. Okay, so you start like that. You start like that. Then how do you make the decimal a non-terminating repeating decimal? So there should be, you should not make a digit or a set of digits to repeat. That's one thing. And the digits must go on forever. You should use the dots. So what have I written? Okay. So 0.72, I made sure that it's between these two, 0.71 and 0.81. So 0.72, then 73, 74, 75, and then dots. So it goes on like that, 72, 73, 74, 75, 76, 77, 78. It goes on like that. Anything vague you can write. See here, 0.72, 16, 0032. Just write what you feel like. 117666631, anything, and make sure you put the dots after it. If you don't show this, then this becomes a terminating decimal, which is not an irrational number. It's a rational number. Just start with 0.72, children, and write whatever you want after it. But you should make sure that a digit or a set of digits do not repeat. There should be no pattern. That repeating pattern should not be there in the decimal part. And use the dots. The dots say that it's non-repeating and non-recurring it should be. So make sure. Look at the next example. 80, because between 71 and 81 is 80, no? So I've written 80. I started with 80, then 801, 802, 803, 801, 802, 803, 804, 805 goes on like that. I started with 0.79, which is between 0.71 and 0.81, 0.79. This is 71, this is 81. Right? So 80, 72, 73, 74, 75, 79. So I just wrote 79. Okay, then you can just continue with anything. So 79, I wrote 7907, 790, then 7900, 79000, and so on. 0.79. I put 10, then 7900, 79000. Goes on like that. These are two rational numbers because they have a P by Q form. Find the decimal expansions of the rational numbers by performing the long division. So 5 by 7 is this one. And 9 by 11 is 0.81 recurring. Now just read the first, because this is 0.81, just read the first two digits after the decimal point. So this is like 0.71, 0.81. So between 71 and 81, 0.72, 0.73, 0.74, 0.75, and write anything. Just start like that, 0.71, sorry, 72, 73. Start like that and just write whatever you want after that. You should just make sure that the numbers lie between these two numbers. See, if you start like 0.63, you're wrong. It's not between 71 and 81. If you write 0.63 or if you write 0.063, it's not between these two numbers. You must insert three different irrational numbers between these two. So if you write 0.63, the number you write may be a non-terminating, non-repeating decimal, but it should lie in this range. If you write 631, 632, 633 and put dots after this, yeah, it is an example of a non-terminating, non-repeating decimal, but it is not in this range. It's not between 5 by 7 and 9 by 11. So you're wrong. Or if you write 1 point, if you write 1 point something, this is 0.71, 0.81. So you cannot write 1 point something. Yeah. Just write the digit under the bar, you know, you must write the digits that repeat only once. You should not repeat it. 714285. The same thing repeats, right? So don't write the repetition, you shouldn't show under the bar. 0.81. 0.81 recurring. You should not write 0.818181 recurring like this. Even if you find something like this, it is nothing but 0.81 recurring. Okay. Am I clear, children?
Yes, ma'am.
Yes, ma'am.
Yeah. So division, I said, don't stop because you're tired of dividing. Don't stop like that. You must wait till the remainder, till a remainder or a set of remainders repeat themselves. So as I told you here, 5 repeats. So I just confirm with one more step. 1 again. See 5, 1, 5, 1. So stop there. When you look at the quotient, you will find that the a digit or a set of digits in the quotient have also repeated. Here also 9 2, 9 2. Yeah, repeats. So stop. Then, so once the remainders repeat, then stop the division process. Till then, you should go on. How many irrational numbers? How many irrational numbers lie between √2 and √3? Now here we had to insert irrationals between two rational numbers. In this question, we had to insert irrationals between two rational numbers. Okay, and how did we insert irrationals? We made sure that the examples are non-terminating, non-repeating decimals. To write an irrational number, you must write a non-terminating, non-repeating decimal. Non-terminating, non-repeating. That's an irrational number. So here, how many irrational numbers lie between √2 and √3? √2 is irrational. √3 is irrational. So they are asking you how many irrational numbers lie between these two irrationals. √2 is irrational because 2 is an imperfect square. 3 is also an imperfect square. So the square root of 2 and square root of 3 are clearly irrational numbers. So between these two irrationals, how many irrationals are there? We know that there are infinitely many real numbers between any two given real numbers. So here the answer is infinitely many. Now find any three irrationals between them. Any three irrationals between them. Okay. So you know how to find. For actually here you don't have to show the division because you can just remember √2. √2 is equal to 1.414. √3 is equal to 1.732. Goes on. Okay. Sorry. You can just use the values directly. Remember and use them directly. You don't have to perform the, that square root which we've learned in standard 8. You don't have to show that division. You don't have to. Remember the value of √2. √2 is equal to 1.414 reckoning. √3 is equal to 1.732. Remember these values. And now insert irrationals between them. So there's 414 and 732. Oh, there's so much of space. Like 414 and 732. So you can write 420 and something, 435 and something. Till 732 you can go. You can write 699. See, between 414 and 732, 415, 416, 417, 418, 419, 420, 500, 600, 700. 720, 721, 722. So till 731. So there's a lot of space. So make sure you write 1 point. You cannot write 2 point something. Okay. You cannot write, you should not write 0 point. You should not write 0 point something. No, it should be between these two numbers. So it should be 1 point. 1 point and write a number after 414. 415 say. And it should be before 731, sorry, 732, which is 731. After 414, 415, from there till before 732. So 731. There's so many numbers. Now just start like this. Just write like you can write 416, 417 goes on like this. Then 731, right? Something vague like 61301 and put dots after that. It should be non-terminating and non-repeating and in the range. So we are just concerned about the first three digits. 414. See, nothing like first three digits. Okay, you can even take 1.4 and 1.7. Compare equal number of digits after the decimal point, or you can take 1.41 and 73. 1.414 and 1.732. Take equal number of digits after the decimal point and insert numbers between them. So I have taken 414 and 732. So you can see a 1 point. I've written 516. Can you see between this 414 and 732? I've written 516. I've written 696, 725. Root 2 is irrational. Root 3 is also irrational. And there are many, infinitely many irrationals lying between these two irrationals. So find their decimal values. So remember, in this case, remember them. The value of root 2 and root 3, remember them. And insert non-terminating, non-repeating decimals between these two numbers. This question, insert one rational and one irrational number. Insert one rational and one irrational between these two. So to insert an irrational number, you need the decimal value. A rational number, to insert a rational number, you can use the LCM method. Or you can also divide, find the decimal value and insert. To insert an irrational number, you definitely need the decimal value of 1 by 6 and 2 by 7. So 1 by 6, the decimal value of 1 by 6 is 0.16666, which means 0.16 recurring. To insert an irrational number between these two numbers, you need their decimal values. So you have to perform the long division and find the decimal expansion of 1 by 6. So you get 0.1666, 0.16 going on forever. So that's nothing but 0.16 recurring, the bar on top of 6. 2 by 7 is 285714, 285714 going on forever. So 285714 and a bar on it. So if you take the first two digits, it's 0.16 and here it is 0.28. If you take the first two digits, it's 0.16 and 0.28. Now insert a rational number, terminating decimal. Rational number. So you can insert a terminating decimal. So between 0.16 and 0.28, you can write 0.17 also. I've written 0.21. Write a terminating decimal to insert a rational number. So 0.21, which is 21 by 100. So 21 by 100 is a rational number between these two numbers. And one irrational. So I've just started with 0.19. 17 and 2 1. No, so 19. I wrote 19, 199, 1999, goes on like that. Find the decimal expansions of 1 by 6 and 2 by 7. That's the first step. And compare, just to understand, compare equal number of digits after the decimal point. So here, like this, here, like this. And between 0.16 and 28, we have 0.17, 0.18, 0.19, 0.20, 0.21. So I have written 0.21. Rational number should be terminating or non-terminating repeating. Now don't take that. Take a terminating decimal. So 0.21. Put it in the P by Q form, 21 by 100. So done with rational number, inserting a rational number. Now irrational number. So I start with 0.19. Irrational, so it should be non-terminating. That's why the dots. And non-repeating. So there should be no pattern. 19, 199, 1999. It's not a repeating pattern. You might say that there is a pattern there. Yeah, 19, 199, 1999 is a pattern. It's not a repeating pattern, no? It's different. The pattern is different. 19, then 199, then 1999. It's a different thing. We don't have a repeating pattern. It's not 19, 19, 19. So it's non-terminating, but I'm sorry, it's non-terminating and non-recurring. Yeah, go through this one. I asked for the working of that answer. Nobody shared. Aishwarya's texted. Oh, Aishwarya's sent. Okay, I didn't notice. Sorry. Only Aishwarya shared that answer. Good. The next one. So I've treated them as 212 and 202. 202, 212. So I've written 203 and 210. You can even write 209. You'll have to insert two rational numbers. So terminating decimal. Terminating. 202, 212. So 203, 204, 205, 206. So 0.203 and 210, 210. Then put, these are terminating decimal. Write them in their P by Q form. And then simplify if possible. So here you can cancel the 0, 21 by 100. Children, because I should have actually shared the images with you at the end of the previous class, that is after the class on Friday. Can you just hold on for some more time and take screenshots? All of you?
Okay, ma'am.
All of you can take screenshots, right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
All right, children. Very good. Yeah. Let me show you from the beginning. It will take some time. Many slides. The introduction part I shared.
Ma'am, can you please send those slides to me? I'm in my grandmom's home and my grandmom's phone is not that advanced. So can you please send those pictures to me? To my mom's phone or my mom's number? Please.
No, you cannot take screenshots now.
No, ma'am. I can't, ma'am.
Okay, in that case, I'll share it with everybody. Okay, fine. I'll send it for you later. Shreya, the others can take it at least.
Thank you, ma'am.
Yeah. Yeah, children, don't take, you don't have to take the screenshots of all the slides. Take only, I'll just tell you, wherever I tell you, children, because you don't have to take the screenshots of these question slides alone. See this one is only the question slide. Why do you unnecessarily take a screenshot of these? So we'll start from here. Done?
Yes, ma'am. Taken.
Yes, ma'am.
This is the next one. Done?
Yes, ma'am.
Yes, ma'am.
Yeah, this is the next one.
Ma'am, should we write these in our class workbook?
Yes.
Okay.
You don't have to repeat writing the heading everywhere. In the slides here, you can see the heading written for every sub questions. Don't do that. Children, I think it will take quite a while. I don't want to hold you for that long. I'm anyways sending it on the group. I think all of you can make use of that. But if you wish to stay and take screenshots, you can do it. I am taking photos myself and putting it in the group on WhatsApp. If you wish to stay back and take screenshots, please do that. But you're also getting it on WhatsApp. If that's enough for you, you can leave the meeting. Okay, so that's it for today's session, children. Thank you. Good night. Yeah, you can choose to stay back if you want to take screenshots. Yeah, thank you, children. Yeah.
Thank you.
Thank you,
Thanks,
ma'am.
children. Thank you, children. Thank you.
Thank you.
Thank you.